Yeah, hello. So we'll start the discussion. Mm, Actually, because of this Janmashtami festival, uh, there is some background noise, but yeah, we can't do anything about it. I have, I have closed all of my windows, etc. Anything, but still, I mean, it's a celebration, so yeah, what can we do? And I was not aware of this, so like shifting this class last moment is also not possible. So anyway, we'll start. So this is regarding week 5. So this is like the first lecture of after metal casting, and this lecture will be more or less. I mean this plus next three. So total 4 lectures will be more or less focused on the metal forming basics and other important concepts related to metal forming. And since metal forming is basically deforming the metal and then achieving your desired end product. So that's why professor has talked about basics of something such as stress and strain, and elastic plastic behavior, etc. And these are important concepts. I would say more important for you know uh, strength of materials class discussion, but this is like basics for our metal forming discussions. So this is discussed not into the depth at which is you know uh, is discussed in strength of material class, but typically you know uh, whatever is up to basic minimum required in this class they are discussing. So we'll also discuss some things about stress and those and then there was some discussion on Mohr circle, so that gives you a general formula to calculate normal stresses and shear stresses on a plane which is tilted by angle theta in the stress plane, and it gets tilted by 2 theta in the Mohr's plane, etc. And keep in mind, when you draw Mohr's circle, it is for one surface. Okay, so like whatever normal stresses and shear stress is acting on a surface, so one Mohr circle is for one surface. So if you have a cube or parallelepiped, then you'll have 6 surfaces, and basically you need to draw Mohr circle for each surface. Okay, so that's how it goes. And yeah, other than that, there were some discussion on stress strain relationships. You know, uh, those things are there. So we'll see some stress strain plots or curves for important materials such as mild steel, aluminium, or any brittle material, etc. And then there is something called as engineering stress strain and true stress strain curves, etc. So and you know some important concepts are there. Apart from that, yeah, 1 second. Yeah, so okay, so we'll discuss those things one by one. So let's get started. And again, I'm telling that these things are more seriously or more involved and taught like that in strength of materials class. But since we are our basic objective is to learn production processes and that one of the process is metal forming, and for that we need to have some basic understanding of these stress strain things, and that is what our objective is. So we are not going into that detail as the strength of materials course, but yeah, we'll see. It's not like we are not doing much. Okay, let's start. uh, yeah, so uh, it was discussed in the class also that when you have a 3D fluid element. Okay, so in that case you draw like shear stress and principal stress or normal stresses like that. But you should before going there you should know some basics about these things. So let me just see. I have some slides from my previous study material. Okay, so we'll first half of the class we'll discuss about the stress strain and other things, and then we'll see the stress strain curves. Okay, so that is how we'll go about this. And first of all, when we talk about stress, so basically you should know stress, what is the meaning of stress. So stress, see, almost everybody knows that stress is force by area, but that's mathematical definition, and that everybody knows. But the physical significance of something which is called as stress is different, and it is given as stress is the internal or external resistance offered by a body against deformation. Okay, so there has to be a deformation, then only stress develops. But there is a catch here. Not all deformations result in stress. No? So there is a catch here. If deformation or strain is free to occur in any direction, then stress will not develop in that direction. So if you have, for example, if you have a rod like this, and you are applying a tensile stress or force is P. So based on this cross sectional area, you are basically applying a normal P by A stress. But you know uh, if there is no resistance from this rod, so that stress is not developed. And very classic case is not in terms of metal forming, but when you study thermal stresses, right? So in that case, what happens? This as in case of thermal stresses, as temperature increases, this length also increases, right? But that does not result in any stresses or anything. Okay, the stress will come only when you have certain restriction on the expansion. So if you don't allow x direction expansion, then there will be resistance offered by the walls to the expansion, and then the stress develops. Okay, so in case of thermal stresses or in case of any other stresses, if there is no restriction, there is no stress. If there is a restriction, there is a stress. Okay, so there are some classifications of yeah, I will just say, I will write this: no restriction, no stress. Okay, so that is the thing. Then there is a classification of stress. you know Not all stresses are of similar nature. Okay, so the broad classification is in terms of normal stress, and the second one is shear or tangential stress. So these classifications are there. In normal also there are two types. One is called as direct normal and another is called as bending. So direct normal stress and bending stress. This is because of due to axial force and due to bending moment. Okay, so these kind of stresses develop because of these reasons. And when I say axial force, so that means if you have a rod fixed at one end like this, and if you are stretching it, so this is a uh, you know uh, in some cases what happens uh, when you have a bending of your this thing, what you call surface. For example, you have a rod like this and you don't apply the direct normal stresses at the center of the rod. What you do, so if this is the center line, you do one thing, you apply the forces in this direction. Okay, so if this is your force direction, so in this case what happens, these are direct stresses only or normal stresses, but they are not at the center line. So because of that, there is a bending moment. So that is the reason. That is the difference. So there will be a bending moment like this, and the top surface will become contracting, and the bottom surface will elongate. That's why you'll have something like this. Your final shape will become something like this. Okay? Something like this it will become. So this is called as sagging, hogging, etc. And those things are taught more in you know uh, solid mechanics class, but this is also a normal stress. Okay, so this your center line also bends accordingly like this. And then coming to the tangential stresses, you know first is tangential stress developing because of direct normal stress. Direct normal stress, because of this direct normal stress, what happens, shear force is developed. Okay, so in some cases this can also happen, and we'll see you know uh, when that happens. So for example, if you have a simple case where you have a bar like this which is fixed at one end, and instead of applying axial force, you apply a force which is perpendicular to the axial direction. So this is your axial direction, right? So you basically apply a force P in a axial direction, and in that case there will be a shear force on this surface. Okay, so this is a shear force or shear stress because of direct normal stress applied perpendicular to the axial direction. Okay, so this is called as directional normal stress resulting in a shear stress. And then there is a fourth category which is torsional shear stress. Torsional shear stress. So in this case basically you apply a torque, and torque is also called as angular moment. So I'll write it due to angular moment, or torque is the most common name for such thing. So in this case, what we do is typically you'll have a bar, let's say a circular cross-sectional bar, and you'll twist it basically. This, let's say this is a fixed at one end, and then in this case typically apply a torque. So like this, you know the directions can be different, but this is how you typically to apply the torque at the end. And as you can imagine, this will result in such kind of torsional deformation in the rod, and that results in torsional shear stresses. Okay, so those things are you know discussed more in depth in strength of mechanics class, but I just introduced here because since we are talking about stresses and strains, you should know what type of stress and what type of strains are there. Okay, so this is the basics about stress. And then there are some formulas, etc. Those things are there, but not the part of this discussion. For example, this torsional stress is given by tau by r equal to T by IP equal to G theta by L. The direct shear stress is given by tau equal to SA y bar by IB. Those things are there, but again, not important for this class. Maybe if you are studying strength of materials, you should keep those things in mind. Okay, and they are usually taught as separate chapters there. Okay? And this normal stress. Usually, what we do is if you are studying within elastic limits or proportional limits, you have this normal stress will be proportional to normal strain. Like this is, there is an assumption here. There are a lot of assumptions, but the most important one is within elastic limits. And this is where we mostly deal, because in plastic limits or in plastic deformation cases, we'll see that towards the end of the class, things are different. So if you are operating within elastic limits, your normal stress will be proportional to the normal strain, and your shear stress will proportional to the shear strain. And then there are different proportionality constants, etc., depending on which case you are talking. If it is a normal stress strain kind of a relationship, you have Young's modulus. This is also called as within proportional limits, because the proportional limit is a correct word. We'll see that in the next half of the class. But typically they are used interchangeably. This elastic and proportional things. So you should remember that also. And other things are, material is homogeneous, isotropic, all those things are assumed. There is no hysteresis, etc. Those things are there. Okay. And then typically we see a 3D stress system. So it is called as a stress strain 3D system. Okay. So in this case, this you must remember from the class, that you'll have a three-dimensional element of your fluid or material that is deforming or undergoing deformation. Like this, let's say. It's a very small element, okay, so that's why the shape can be anything. If you are not satisfied with the cube or parallelepiped, you can take anything, but cube and all makes life easy, because it's a Cartesian coordinate system that we typically adopt for these problems, and that's why we take those kind of things. So if you have a coordinate system, one second. If you have a coordinate system like this, so this is your coordinate system where you have x, y, z axes like this. So in that case, as we know that if you take a normal stress like this, it is called as sigma x, because it is, the normal convention is, if it is tau or sigma, the first subscript and second subscript. First subscripts represent phase, this one represents direction. Okay, so this is the adopted sign convention, and the sign convention is, for, I mean, this is the adopted nomenclature, not sign convention. This sign convention is something different. Sign convention we consider uh, positive phase, positive direction as positive. Let me just see. Yeah, that is, I think, for shear stress. Yeah, I mean, sign convention for normal stresses is tensile, or basically if you are pulling your surface outward, that is positive, and if it is a compressive normal stress such as hydrostatic force or pressure, then it will be negative. That is for normal stresses. For shear stresses, uh, you know it is, as far as I remember, it is positive, 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 negative, negative, positive. Yeah. So for shear stresses, it is you have four options for that. So depends on what phase you are operating, and in which direction on that phase. Okay. So by default, these are the positive directions, okay, in our Cartesian coordinate systems. So if you are operating on a positive phase, I mean, the, the normal to the phase is the direction of a phase. So if that normal is positive and direction of your shear stress is also along the positive direction, then your shear stress is positive. If both of them are negative, it is also positive. But if they differ in sign, it is negative. Then, for example, if you consider, let's say, uh, surface 1, you know, one second, I pressed something. Okay, if you look at, okay, first we'll define the directions on this main guy. Okay. Okay, so in this case, you'll have two shear stresses on that sigma xx plane. Second, yeah, so one shear stress will be along this direction, and one shear stress will be along this direction on this plane. Similarly, here you'll have this normal direction. So this will be your sigma y. It is z, right? So it will be sigma zz. Then you'll have one shear stress in this direction. That will be your tau. And first is phase. So this is a z directional phase, and it is pointing towards positive x direction. So this will be tau zx. Similarly, this ones will be phase is x and direction is z. So tau xz. This is xy. And yeah, there will be one more guy. This will be tau z y. Similarly, you have to draw those things here. So this will be sigma yy. This will be a tau yx. This will be a tau yz. Okay, so this is your uh, stress system, and you'll have equivalent strain system also. But there are 9 components, 3 are normal, 6 are shear. But typically we assume something called as equilibrium and that also includes the angular equilibrium, and therefore this pair of these stresses are same shear stresses. Okay, so before that, you know, consider, let's talk about this. So you have, let's say, this tau xy as a shear, tau yx as the shear direction, and correspondingly you have tau xy, right? From this figure you can see, from our main uh, system, 3D system. So this tau xy is acting on the surface whose normal is in positive direction, as well as it is pointing in a positive y direction. So therefore this will be positive. Similarly, tau yx, positive y normal, positive x direction, this will be positive. Okay, and the counterpart to this will be your stress system like this. So this is nothing but on the back side of this plane it will be tau xy and tau yx. Okay, there won't be any equilibrium, and these will also be positive. Okay, whereas if you consider, yeah, I mean, we have shown all the positive shear stresses here. Okay, so negative ones are in the opposite direction to the current ones. Okay, for example, what I mean is, if your tau xy, or tau yx, if it is in this direction, that means that it is on the positive phase, but it is pointing to the negative x direction. So this will be negative, okay, in those cases. But the cases that we have shown with black color, they are all positive shear stress directions. Okay, so therefore you should remember those things, because in many gate problems they will not mention the direction. They will just mention that shear stress of 45 MPa is acting on a surface, and then you have to figure out the direction, etc. Okay, so keep those things in mind. And yeah, then yeah, okay, so you should know this also, because of, oh, sorry, angular equilibrium. You can prove tau xy equal to tau yx, and similarly tau xz will be equal to tau zx. In general, this is written as tau ij equal to tau gi. This I and j are called as indices, and this is called as Einstein's initial notation. Okay, so this I comma j, they go from x comma y comma z. Okay. And usually I is not equal to j, then only these are shear stresses, otherwise they become normal stresses. Okay. And because of this, your stress matrix is always symmetrical. Okay, so what I mean by stress matrix, typically it is sigma xx, sigma yy, sigma zz, right? These are your normal stresses. Then you will have tau. Okay, 1 second. Is it tau xy or tau yx here? Actually, it doesn't matter, right? These are same, no? So it should not matter. But ij, so I rho. So yeah, this will be tau xy, tau xz, tau yx, tau yz, tau zx, tau zy. This matrix is always symmetrical because of angular equilibrium assumption. If it is if your system is in equilibrium, then it has to be uh, in equilibrium. Okay, 1 second. our body is in equilibrium. Okay, so if there is no equilibrium, then you can't write this also. Then you have uh, 9 different stresses acting on your body, and then you have to solve it. But in this case, since it's a symmetrical thing, only 6 unknowns are there. So you don't have to find 9 unknowns, you have to only find 6 unknowns. Okay, and this system is also called as Euler-Cauchy stress. I mean, this is given by Cauchy. So this is so this is called as Cauchy stress tensor. And you should know tensor is a one dimensional higher than a vector. So vector needs direction and magnitude, whereas tensor needs direction, magnitude, and a surface on which it acts, okay, on which the force acts. So that is what tensor means. And then what they do is they divide this. See, we know that for every square matrix, uh, you can write it as a combination of symmetric and uh, anti-symmetric matrix. So they write this sigma as one symmetric matrix plus the other anti-symmetric matrix. This is a property of all square matrices that you can have this decomposition. Okay, and then what they do, uh, you know, yeah. But before that, okay, one second. There are some invariants. Okay, so before decomposition, we'll saw some invariants are there. So this, sigma matrix, it has 3 invariants, and these invariants mean independent of orientation of stresses. Okay, so there are some properties which are independent of orientation of your stresses or surfaces of your body. They are called as invariants. Okay, so first invariant for your stress matrix is called as I1. It is nothing but sum of your principal diagonal elements. In this case, it will be this, and it is always constant. Okay, so this is also called as trace of this matrix, and it doesn't matter whether it's a principal plane or any other plane on which you are studying the forces or stresses. The invariant will always be constant. So trace of your stress tensor will be always constant. Second invariant is called as I2, and it basically is a sum of minors, second minors. Okay, so if you want to write it in the form, it is sigma xx sigma yy plus sigma yy sigma zz plus sigma xx sigma zz. So these are multiplication of your normal stress minus tau xy square minus tau yz square minus tau zx square. So this is your second invariant. It will be always constant for any orientation of your body along, with some theta or anything. This is nothing but, in another form it is written as, okay, I will not give that because it doesn't matter, but you can keep in mind that the, product of your uh, normal stresses, 2 at a time, plus sum of that 3 terms, minus square of your shear stresses, and sum of that is the invariant. And third invariant is I3, which is nothing but determinant of your sigma. So determinant is always constant. Okay, so on any plane, if you are doing the stress analysis, these things have to be constant. Okay, and this is nothing but basically these are eigenvalues calculations. So what typically done is, uh, you try to find the eigenvalues of your sigma matrix, and this characteristic equation of sigma matrix is nothing but minus lambda cube plus I1 lambda square minus I2 lambda plus I3 equal to 0. And this is nothing but, see, when you say characteristic equation, it is nothing but you take the determinant of sigma minus lambda I matrix. Okay, so that's the coefficients of your lambda in your characteristic equations are your invariants, and that is true for strain matrix also. This is for stress matrix. Later on you'll see, you divide this into two parts, as I said. One is called as mean. Yeah, so we'll talk about the decomposition. So this sigma is divided into two parts, which is called as, first is called as mean or volumetric stress tensor. This is the symmetric part, plus the second component is called as deviatoric stress tensor, deviatoric. Deviatoric. Okay, so this is your antisymmetric tensor or matrix. Okay, so this guy and this guy, you can write them simply as following. Yeah, basically you subtract this sigma mean is nothing but the sigma matrix is written as so let me just confirm once. One second, I have a doubt whether you subtract the whole thing or yeah, I mean, the reason is, as far as I remember, this mean matrix is, it only has hydrostatic, so basically principal diagonal elements. It doesn't have those things. Yeah, so basically this hydrostatic or volumetric 1 second. Huh? Yeah, actually, I made a mistake. It's not anti-symmetric, it's also symmetric matrix. No, this is the distinction is this is responsible for volume changes. I mean, this part of your stress is responsible for volume changes, and this part of your stresses is responsible for shear deformation. Okay, so this is also, I mean, I mean that classification is different. Okay, symmetric and this uh, you know other things. But when you call it as a deviatric, it is basically shear deformation related. So basically, this will have you know sigma one by, I mean, sigma mean, right? This deformation, it basically is sigma mean 0 0 0 sigma mean 0 0 0 sigma mean plus this will have sigma xx minus sigma mean tau xy tau xz tau yx tau yx sigma xx minus sigma mean tau yz tau zx, this is tau zx, sorry, tau zy and this will be sigma z z minus sigma m, and sigma m is nothing but first invariant by 3. So this is basically sigma xx sigma yy sigma zz by 3. Okay, so this is the decomposition of your stress matrix. Okay, pardon that, it will not be anti-symmetric, it will be symmetric only, but it is responsible for the uh, this thing, you know, uh, volumetric and shear decomposition. And similarly, you'll have strain matrix. Uh, you know strain matrix. 1 second, let me think about it. Yeah, so now this is about stress matrix. Then you'll have a 3D strain matrix. in this case, what happens? You can understand this with uh, one example. You know, uh, there are two types of strains here. One is linear strain and one is angular strain. Because you have initially this kind of surface, let's say. I mean, you have to draw this in 3D, doesn't matter, but the idea is same. You have, let's say, such surface, and you have, and this shear stresses are, typically sometimes they are shown by half arrows also, arrows with half heads. That is also possible. Tau ix, tau xy, tau xy, and tau ix. Okay, so this is a positive pair of shear stresses. But when it deforms, it looks, this element will look something like this. Okay. So again, if you have your coordinate system like this, in equilibrium, what happens? This angle will be same as this angle. Okay, so this is called as some phi xy by 2, and this angle is something called as phi yx by 2. So these angles have to be same in equilibrium. Okay, and this is still the same direction of shear stresses. Okay, so these because of the equality of shear stresses, this angle deformation is also same. So it will deform by same angle from your vertical axis or something like that. Okay, so this is called as shear strain on a surface. So this is for one surface. So then if you write it in a 3D form, so this will be your strain matrix. It will have again principals strains. So these are nothing but strains resulting because of only the normal stresses, which are sigma x, sigma y, sigma z, z. They don't contribute to any shear deformation, but you'll have this shear deformations here, like this. So this half will be accompanying them. Okay, so this becomes x z by 2. This will be a phi z x by 2. This will be a phi z y by 2. This will be a phi y z by 2. Okay, so this is your strain matrix. So only difference is here this 1 by 2 1 by 2 comes with every this thing of diagonal element. Okay, in stress matrix it doesn't happen that way. And then they find some ways to replace all these things. So those things are there. And again, you can divide this strain matrix also in mean or volumetric strain matrix and a deviatoric strain matrix. Okay, so those things are there. I mean, that is similar, so we'll not again go into that, but it's a similar transformation. Okay, so yeah, and then there will be some invariants for strain matrix also. Okay, so those things are there. Okay. Just see the other form. And then they further write this in some other form, and that is in terms of deformations along x and y and w z direction. So basically, then they consider x direction deformation as u, y direction as v, and z direction as w, and then you can further simplify this, right? So this becomes del u by del x. So this u is nothing but displacement along the x direction of your fluid element. V is displacement along y direction, and w is displacement along z direction. and then you write the other components as half into del u by del y plus del u by del z. Okay, so this will be your epsilon 1 2. Okay, 1 second. U by y, that is correct, and it will be v by x. Okay, so this will be v by x, and same component will be here. Okay, del u by del y plus del v by del x. Okay. Similarly, this, because this is also symmetric matrix, so this will be u by z plus w by x. Same component will be here, u by z, w by x, and this guy will be v by z plus w by y. Okay, so you can keep playing around in these things, depending on what is asked in the problems. You have to uh, sort things out. Okay, so this is the introduction part. Then okay, this is all fine, but then you need to calculate some things, right? I mean, so there is something called as Hooke's law. Okay, so uh, you know Hooke's law is used. So Hooke's law, as I said, it is valid for homogeneous isotropic uh, isotropic materials within proportional limit, or sometimes they call this proportional limit as elastic limit also, as your stress will be, so we are talking about linear stresses here, not the shear stresses. I mean general stress. Okay, so I mean like normal stresses. Okay, so that will be equal to your strain. So you have this Young's modulus as a proportionality constant. This is your Young's modulus, and it's a material property. Okay, and then what you do is basically when you have a 3D system, you have stresses in x, y, z direction, strains in x, y, z direction, right? So there you basically uh, you know see, if it is a 1D case, in 1D case, let's say you have only x direction deformation, your sigma x will be Young's modulus into the x x strain, right? But if it is a 2D case, what happens? It's not that straightforward, right? Because uh, you know uh, in that case you have uh, two directional deformation. Okay, so there this Poisson's ratio come into the picture. Okay, so this Poisson's ratio, even for 3D cases, this Poisson's ratio is important. Poisson's ratio, which is typically mu or nu is used. I'll use mu. Doesn't matter. It should be consistent. That's all. It is lateral strain by longitudinal strain. Okay, so now the direction of strain is defined based on the stress or the force that is applied. For example, a classic problem of, let's say, a rod is there of diameter d and length, let's say, L. Okay, so and it is getting pulled in x direction, let's say only one directional case, no sorry 2D case. So in that case what happens, length increases, so the delta L will be positive, but since volume is constant, the delta in diameter will be reducing, right? And that is why the negative sign comes in the definition. So your mu will be, see, longitudinal axis is along the application of normal stress, that will be your length axis, So your longitudinal strain will be delta L by L, and your lateral strain will be delta D by D. So this is how you calculate your Poisson's ratio. In the context of lateral and longitudinal, uh, you know, uh, if it is a 3D case, then again you have to take it by face-to-face basis, basically, because there, you don't have. 1 second. 1 second. Yeah, I think in 3D cases, this lateral strain includes two directional strains. Longitudinal will be one, and other two directional will be lateral. Okay? So just let me confirm. Yeah, 1 second, guys. Because if it's a 3D case, as far as I remember, uh, you have to take the lateral strain in other two directions. Because longitudinal remains the same, right? Yeah. So in 3D direction, you have to take two lateral strains and divided by longitudinal strain. Okay, and those two directional lateral strains will be negative only, because when you pull something, the other two sides tend to shrink to maintain the volume constant. Okay, so that is how it changes in the 3D case. Okay, so I'll just write for a general 3D case how to apply Hooke's law, because in many problems they tend to ask these things, especially for GATE exam. Maybe not the part of material science or theory of production course, but you have this SOM. It's a part of SOM, but we are discussing it here today. So this is your first 1D case, but you just mix it up with the this is will be your sigma sigma, sigma x sigma y. So basically your normal stresses z by e. Okay, so basically 1 by e sigma x x minus sigma y y minus mu into sigma z z. This will be strain, this will be your sigma xx basically. So this is again linear strain. Okay, so not the angular ones. Okay, these are not the angular ones. So similarly, you will have sigma yy as 1 by e sigma yy minus mu sigma x x minus mu sigma z z, and this z z will be 1 by e sigma z z minus mu x x minus mu y y. Okay, so this is a general strain thing, and we have something called as volumetric strain. Let's say epsilon w. That is, I think, some of these three. Yeah, it is x x y y plus z z, and if you add these things, you will get this as sigma x x sigma y y sigma z z by Young's modulus into 1 minus 2 mu. Okay, so if mu is 0.5, your volumetric strain is 0. This is a famous GATE exam question, and that means whatever longitudinal strain you get in one direction, the two lateral strains in another two directions, so net volume change for your body is 0. Okay, that is one thing. And then there are some other things like bulk modulus and like Young's modulus, you have shear modulus and bulk modulus. So bulk modulus, it is used in fluid mechanics also, but since we are talking about metals or solids here, this is typically denoted by K symbol. It is usually change in pressure or application of pressure, which results in how much volume change, fractional volume change. This is the definition. And usually when you compress something, when you apply pressure, it volume reduces. So to make the ratio positive, negative sign is there. And similarly, you have one shear modulus, which is also called as modulus of rigidity or something like that. But this is represented by G, and it's nothing but shear stress by shear strain. Okay, so Young's modulus is normal stress by normal strain. So this is its counterpart in the shear case. So we saw earlier, right, in what cases shear stress and shear strain develops. Okay, and this Poisson's ratio, there are some practical ranges. Okay, it's not like it can be anything. For cork, it is 0. That's again important question. And when I said this 0.5, it is for perfectly elastic material. 0.5 Poisson's ratio. But in reality, rubber has a Poisson's ratio of almost 0.48. So, in reality, if somebody asks you what is the perfectly elastic material, it has to be rubber. Okay. And the other elastic materials that we have, like, steel, aluminum, etc. Elastic materials, their value, there is a range like 0.25 to 0.4 to something like that. So it's a range. Okay, so things change in between. And if you have a brittle material like concrete or anything, it will have a smaller Poisson's ratio. So concrete has 0.1 to 0.2. Okay, so the more the brittle material, less will be the Poisson's ratio. That also one way to remember these things. Okay, and then we were talking about these guys, and there are some correlations which are famous for some competitive exams or something like that. But you can remember this one line and your life will be easy. So E is 3k minus 3k into 1 minus 2 mu equal to 2g into 1 plus mu. That's it. Then, if in exam they want the relation between, uh, you know, k and g or whatever it is, you can do that on your own. I think in your assignment also they have asked one question on this. I think you can solve this. Let me just see. Yeah, they have asked the relation between K and E. So that is directly given here itself. In terms of mu, they are asking. Okay. Yeah. Yeah, I mean, you can, but this is important one, okay? If you remember this, then you can solve any type of problems that is asked from these correlations, etc. Okay. Okay, then let's move on. Then we'll go to the Mohr circle because that is also important because it gives you a generalized thing to uh, denote some things, right? Let me just see before that if you have any other things. Yeah, these are Then the Mohr circle is the important one. Let's go there. Or yeah, it basically it comes under the topic name, which is called as transformation of stress and strain. Okay, so that is what it is. So basically, this general case. For example, if you have a square, your element like this, and let's say there is a sigma xx is your normal stress, sigma yy is your normal stress on this plane, okay? And you'll have similar on the other side, okay, because the body has to be in equilibrium. And let's say you have this shear stress components like this, let's say tau xy, because it will be equal to tau yx, so they are not going there. One second. Yeah, so in that case, there is a general formula, like if you have like this, if this system is now, if this element is now rotated by some angle, so let's say it becomes like this. Oh, sorry. It is making it hexagon. That's good, like new thing to know. Anyway, you tilted this element basically without any deformation or anything, and now it's tilted by some angle theta. So basically you take this angle with your vertical. Okay, so this element is tilted by this theta in this direction. So in that case, now you'll have some new stresses, right? So it will be sigma x dash. This guy will be, and they will be again balanced. So it will be sigma y dash, and you'll have some form of sigma tau xy dash. So this will be your new stress system. Okay, so you have to do some derivations, and there are some standard formulas to get these things based on your theta. So this becomes sigma xx plus sigma yy by 2 plus sigma x minus, this will be xx minus sigma yy by 2 into cos 2 theta. Okay, remember it's 2 theta, okay, not theta. Tau xy into sine 2 theta. And your another principal stress or normal stress will be, you have to just replace theta by 90 plus theta in this formula. So because that another stress is nothing but at 90 degrees ahead of your sigma xx dash. So this becomes, see, the constants remain same only because cos 2 theta plus 90 is minus cos 2 theta, so therefore this becomes minus, and sine 2 theta plus 90 is minus sine 2 theta, so this becomes minus. Okay. And then you have your tau dash xy is given by minus sigma x minus sigma, this will be xx minus sigma yy by 2 into sine 2 theta plus tau xy to cos 2 theta. Okay, so yeah, difficult to remember the, I mean, it's a lengthy formula, but if you solve some problems, you'll remember it. Okay. So what they do typically, uh, these three equations are there, and they try to find the principal planes. Principal planes basically are defined as, they will have zero shear stress, so, and only normal stresses. They are called as principal normal stresses. So this guy has to go to 0 on this, in this case, and if you just use this tau xy dash equation, you'll get the condition as tan 2 theta p. P represents uh, inclination and angle of your principal plane direction by sigma xx minus sigma yy. Okay, so then based on your tan inverse of this RHS, you get the theta p value. So get theta p value and then substitute in sigma xx dash and sigma yy dash formula to get principal stresses. Okay, so these are called as principal normal stresses. Let me just confirm one thing about this. One second. Yeah. So then if you do that, what you'll realize is you get the principal stresses. Let's say sigma 1 and sigma 2. So these are your principal normal stresses as sigma xx plus sigma yy by 2 plus minus under root sigma xx minus sigma yy by 2 whole square plus tau xy whole square. Okay, so this is how you get your principal normal stresses, or they are called as principal. One is called as maximum principal if you put the plus sign. Another one is called as minimum principal or minor principal. Okay, and we know that our from our first invariant, this summation of your normal stresses on any plane is always same. Okay, so this has to equal to this, and this has to equal to this. Okay, so this comes from your invariant one definition. And then there is another case to find. So this is the maximum value of your normal stresses at theta p plane. Okay, theta p inclination plane. But sometimes they ask to find maximum value of tau xy. Okay, so this is called as maximum shear stress. Okay, so what is there? This maximum shear stress plane. This maximum shear stress plane is at 45 degrees to your theta p. So wherever you have maximum principal normal stress plane, if you add 45 to it, you'll get maximum shear stress plane. Okay, and then you get tau max as uh, you know basically you have to again do the same thing, and in the tau xy dash formula here, let's say this equation star, here you have to put theta p plus 45, and that will give you your maximum shear stress value, and it comes as tau max as this bracket sigma xx minus sigma yy square by 2 is there, by 2 and whole square plus tau xy square. But that is not important. If you do further simplification, you get tau max as mod of sigma 1 minus sigma 2 by 2. And this is a famous 1-mark question in many competitive exams. Okay, so maximum value of your shear stress is nothing but magnitude of your difference in your principal stress, normal stress values divided by 2. Okay, so And if you draw these planes, so so what happens, let's say you had this system, right? So this was your initial system where you had sigma xx, sigma yy, and you had some tau xy component, and then this is your tau, and then you, let's say, tilted it by, let's say, angle theta p. Okay, so this is, and this inclination is always from your vertical line. Okay, so if you do that, let's say you incline this by theta p. So if you do that, you get uh, your principal stress, right? So then your system becomes, or your element will become something like this. Okay, and this will be your sigma 1, sigma 2, and similarly you'll have balancing ones. There will be no shear stress on principal plane because this is a theta p direction. And then this is your uh, principal plane condition. Okay, and then what you have to do, you have to tilt this by next 45 degrees Celsius. So if let's say this is your 45 degrees Celsius angle, and in that case now your system becomes like this, something like this. Okay, there is no deformation. Okay, you're just tilting your system. So this is the condition for your maximum shear stress, but there will be some some normal stress also in these cases. Okay, so it's not like, see, in case of principal normal stress, the shear stress is zero, but for maximum shear stress, principal stresses are not zero. Okay, so this will be the case with your tau max. Okay, and we know that this will be sigma 1 minus sigma 2 by 2 mod. Okay, and this value of your principal stresses will be same. Okay, so you'll have this sigma x plus sigma y by 2, and from our I1 property we know this will be just sigma 1 by sigma 2 by 2, sigma 1 plus sigma 2 by 2. Okay, so this is the case of your maximum shear stress plane. Okay, so you have to remember it this way. And yeah, everywhere you'll have some balancing shear stress, etc. Those things are understood. Here also, here you'll have some balancing stresses like this. Okay, so these things are understood. But yeah, this is a very important diagram. You should remember everything that is shown here. It's very important. Okay. Yeah, and sometimes what they do, they give you the initial condition as, this is a special case of initial case of pure shear. Okay, so basically at the start only they will mention that you only have shear stresses in your body. There are no normal stresses here. And then what happens when you rotate this by, sorry, so some theta p angle. So in that case, what happens? In that case, there will be some development of normal stresses, and there will be some shear stress also. Okay, and if you use the formulas that were given previously, this will become tau xy sine 2 theta, and this tau xy dash is tau xy cos 2 theta, and your sigma yy dash becomes minus tau xy sine theta. See, minus means it will be a compressive. Plus means it's a this thing. And in this case, if they ask you what is the principal plane, so you have to take this as 0 and get theta p. And you see here, if you do that, you just get theta p as 45 degrees or 135 degrees. So that will be your principal strain, principal direction, theta p. And your principal stresses come out to be tau xy and minus tau xy. And similarly, if you put theta p plus 45 in your tau xy dash formula, you get tau max. This is different than your principal plane. This is tau max. That is sigma 1 minus sigma 2 by 2. It's again just tau xy. Okay, so these kind of things are there, and what do you say? Usually, I mean, these things, if you understood well, then it's fine. But the most simple way to solve this is by drawing a Mohr circle. So basically, what happens? These invariants, etc. If you study them thoroughly, you will realize that it basically is nothing but equation of circle. Okay. So what I mean by that is, yeah. So you have something called as Mohr circle. This is nothing but easier representation of the formulas that we just studied. Okay. And the derivation is not that difficult if you just think about it. So you have this sigma x dash formula as sigma xx plus sigma yy by 2, or I'll just copy it. No need to write everything again. Yeah, this first formula, right? Okay, so and you have this tau xy dash like this. And what they do, they basically square these two equations and add, and then simplify. And then in that case, what happens? This sigma xx dash square plus tau xy dash square, and you have to do some before doing the square here, you have to do some simplification. So this minus sigma xx plus sigma yy by 2 whole square, and then you add the tau xy dash square, and this becomes sigma xx minus sigma yy by 2 whole square plus tau xy whole square. And if you pay attention here, this is nothing but a square equation of a circle. This represents x minus a square plus the other term is, look at this term, this is y square equal to, and last term is r square. So this is the equation of a circle with, this is equation of a circle with x your x-axis is sigma xx dash axis, which is also called as normal stress axis. Your y-axis becomes tau xy dash axis, which is shear stress axis. So this is basically a circle on a shear strain and shear stress and the normal stress plane. So if you draw that, let's say this is something like that, and this is your normal axis and this is your shear axis. Let's say this is your origin where both are 0, and A is A is equal to sigma xx plus sigma yy by 2, and as we know the invariant property, so this is nothing but I1 by 2. So that invariant, so any two principles or normal stresses, if you know, that summation by 2 you have to do. This is your gives the center, circle center at a comma 0, because y don't have any constant in the square term. So this is a circle with center at some positive, because sigma xx plus sigma yy, assuming let's assume it is greater than 0. In some cases it can be less than 0, but let's assume. So there will be circle like this and center here, and the radius is this. So if you take a square root here, this thing, what do you say? Yeah, 1 second. I need to add a circle now. So what I'll do, I'll draw a circle. There was one option to do circle, no? 1 second. How to add circle? These are all numbers. Shape, very shape. No, this is something else. Okay, anyway, I'll draw it like this. And so this will be your radius. Okay, so this is your Morse circle, and this is the procedure to draw that. Okay, it's a very important topic for your solid mechanics course. Okay, and then there are many things here. Okay, it's a very interesting thing. First and foremost important thing is Morse circle is always drawn for a surface. Okay, so in a 3D body, if you have 6 surfaces, you have to draw 6 Morse circles. Okay, this was a previous year ESE question, so you should remember that. And then you can do further things, such as this will be your tau max, right? Because tau max direction is y direction, so wherever your circle has maximum this thing, you can get tau max. You will get tau max here as well as here. And this will be negative value, and this will be positive value. Okay, this will be your sigma 1, the principal stresses. Correct, no? Because then only it will be maximum stress, right? Principal strain is maximum, no? So therefore it has to be like this. And yeah, so now from here you can note one thing, that your radius has to be equal to tau max. Correct, no? Because radius is constant for all points, and we all know tau max is nothing but sigma 1 minus sigma 2 by 2. So even if you don't want to use this TDS formula for radius, you just calculate principal stresses and just get the radius from that also. That is also fine. That is one. And another thing is, if you have a body like this, and if you rotate it by some angle theta from vertical like this, this translates to 2 theta rotation on Moore's circle. This is a very important point. Okay, students often miss this, that if you rotate your stress plane by theta angle with vertical, by that point on your Moore circle gets shifted by 2 theta p on the Moore circle. Okay. And if you have any random point like this, that will be signified by your stresses sigma x and tau x. X is but nothing but normal thing. Because on a plane you'll have only, on a surface you have only normal stress and a shear stress. Okay, so one point on a Moore circle, a point on Moore's circle represents a plane in actual body on which, let's say this is sigma xx, sigma xx normal and tau xy shear stresses are acting. Okay, so one point on a Moore circle is basically uh, a surface in reality. Okay. Then there are different cases or properties of Moore circle. We'll discuss one by one. And actually strain curves today, but I think we don't have enough time for that. So we'll do that in next class. But the important things are like already taught in the class. We'll again revisit them in the next class. But you should know that there is something called as true strain, true stress, engineering stress, engineering strain. All those things are there, and you have to basically study the correlation between them. This was also given in the class by professor. I think assignment question is also there. And then you have to study different stress strain diagrams for different materials, such as mild steel, non-ferrous things like aluminium, etc., and brittle materials like concrete or gray iron, something like that. Okay. Per class. So, but today we'll close with the Moore circle only, because otherwise we have very less time. Next class maybe we'll take again this uh, stress strain curves. There are important things there also. So let's see. Okay. So now there are many GATE exam questions on Moore circle. Even ESE also there. Even civil services also, if you are having mechanical as the optional. So, or I think in civil also Moore circle should be there somewhere. So they ask in case of pure shear, draw Moore's circle. I mean, this is a crude question, but there are many things about this. So we just saw in case of you know pure shear, these are your principal stresses, and your maximum tau will be equal to tau. So I'm talking about this case. Okay, so the initial pure shear case. So we already saw this. So this will be not tau 2, just tau. So then your center a comma 0 coordinates, how do you calculate them? basically sigma 1 plus sigma 2 by 2, right? So sigma 1 plus sigma 2 by 2 comma 0. This will be 0 comma 0 because summation is 0. And radius is nothing but sigma 1 minus sigma 2 by 2. So that comes out to be tau. So in case of pure shear, the Mohr circle is nothing but a circle with center at origin or 0 point and radius which is equal to principal stress. Yeah, this one is slightly bad, but you understand, right? This will be 0 your center and this will be your radius in case of pure shear. Okay, this is one important question. Other than that, another question is hydrostatic case. Okay. So basically, they'll say that you have a water tank like this, like this. You have a water here, and you have a point inside this water, which is, let's say here. So it is at some height from the surface, right? H or depth it is called. So here, at let's say this point is A. So pressure at A will be P ATM plus rho G H. Okay, let's say assume this is a free surface. So here it is, hydrostatic case. So at point A, the hydrostatic pressure will be compressing the point at A from all the sides. And this is a case where you have compressive stresses, not the tensile ones. And in case of compressive stresses, and we all know that pressure, is equal magnitude always compressive. So your principal stresses, etc., they are all becoming minus PA because it is compressive. Okay, that is one case. And similarly, another case could be you have a pressure vessel like this. This is a pressure vessel with the pressure inside higher than the atmospheric pressure. So high pressure vessel, and there is a point B inside this. Let's say not on, let's don't take it on the inside, let's take it on the surface. Okay, so here what happens, the pressure that it exerts on your pressure vessel boundary, let's say PB, here PB will be significantly higher than PATM. Okay. And it's a tensile stress because it is trying to expand, not contract. Compressive strengths happen in hydrostatic case, whereas in some pressure vessels the boundary experiences tensile stresses. Okay, so how to represent these points on a Mohr circle, that is also sometimes asked. So here you have to, first clue is in these cases there is no shear stress. Okay, of pure normal stresses because pressure is always normal. There is no shear deformation because of pressure. So therefore, this will be your point B, which will be, PB by some area into 0, because this is your positive direction of normal stress. And your point A will lie somewhere here because it will have some negative B by A. Oh, it's a pressure, right? So no need to divide by area here. It's just PB comma 0 and this will be PA comma 0. Okay. So this is how you represent such points on a Mohr circle. So this Mohr circle will have 0 radius and positive and negative center, okay, depending on what pressure it is increasing. Okay, and then they will ask that what are the principal plane directions for these conditions. So there are infinite plane dimensions because there is directions because there is only one point and it can have infinite angles. So like that you have to answer these questions. And this is similar to some another case. Okay, for example, if you have a surface like this which only have compressive stresses sigma 1 sigma 2 like this, so that will also come somewhere here. And if you have a surface with pure uh, tensile stresses like this, that will also come somewhere here. Okay, because there is no shear, no. So if there is no shear, there is y equal to 0 or tau equal to 0. So such cases also lie only on the normal stress axis sigma. Okay, so these things are there. So now before we close, yeah, and since this is not a strength of material class, I'm not going into details, but I'll just give you hints that if you find theta p, theta p is, how do you find it? uh, in Morse circle, what you do, the advantage is you don't need to use those formulas. So let's say you have a point somewhere here given in your problem. Okay, so this point is given. So what you do, you try to uh, go anti-clockwise to the maximum plane. So basically, if you want to find a principal plane for this, you just, what you do is you go by this way. This will be your 2 theta p. Okay, and if you draw this map by a scale, or this figure by scale, you'll get exactly theta p value. No need to do any calculations. And then if you want a shear stress or shear plane, you have to get 2 theta p first, plus you have to add 90 degrees, because in surface it is 45 degrees. On Morse circle, you have to add 90 degrees to your theta b direction. You'll get a maximum shear plane. Okay. And the sign convention that typically follows is, in case of your rotating, this is positive, clockwise is negative, for theta rotation. I mean, these details, if you are interested, you can go and study SOM, but since we are discussing this, I thought I'll give you this. So, I think we are almost at the end of the time. So, let me just see if anything is pending from our circle. No, more or less everything is covered from our circle. Okay. So, one simple problem could be asked like this. And as I said, we'll take that strain and stress uh, you know, plots, etc. in the next class, because today we are running out of time. So let's say a simple problem we can take, which have 50 MPa as a normal stress in x direction, let's say, and in y direction you have sigma ys minus 35 MPa, and your shear stress tau xy. So you need to first find center and radius of Morse circle. Okay, so there are two phases here, no? This is your first phase, this is your second phase, no? 1 second. Huh? Yeah, but I mean, this is the case not like two surfaces, it's different case. This is standard case. So here you have this will be your sigma xx. This is your nothing but sigma yy, and this center will be at A, which will be sigma xx plus sigma yy by 2, right? So that will be 15 by 2, so 7.5. So your center will be at A comma 0, which is 7.5 comma 0, and radius will be mod of sigma 1 minus sigma 2 by 2. So here you can, you need to first find sigma 1 sigma 2, right? So center you found out. Now for the radius is equal to tau max, but tau max needs sigma 1 minus sigma 2 by 2, right? So that you don't have it, no? You don't know sigma 1 sigma 2, right? You know the summation, but you don't know the values. Okay, so therefore you have to use this one, this formula, which is sigma xx minus sigma yy by 2 square. R square is sigma xx minus sigma yy by 2. This will be 50 minus 30, minus minus will become plus, so 85 by 2 square plus 40 square. So you can do this calculation and you'll get the R, which is square root of this. Okay, and that will be your Mohr circle things. Okay, so with this we'll stop for today. We'll continue the discussion on the stress strain things on the next class. Okay, so hopefully this was helpful in some sense, and yeah, we'll continue after this in the next class. Okay. Okay, so